So good morning everyone. Today we'll continue the yesterday's class. So we started the fifth unit, state space analysis. We have few definitions. What is a state? State variable, state vector, state space, and state space equations, and the state variables, input variables, output variables, and the representation of your state variables. Generally, we represent with first order differential equations as a function of state variables and input variables. So we had the functions in terms of state variables and input variables. So state model for LTI systems. So instead of taking a function, we'll take a linear combination of state variables and input variables. The equation is f dot of t is equal to a into x of t plus b into u of t. So it can be written as matrix form. Similarly, for output equations, y of t is equal to c into x of t plus d into u of t. Where p is the number of output variables, m is the number of input variables, n is the number of state variables. So the equation number 1 and 2 are called state model of the system. So for the state model, we have drawn the block diagram. And state model for SISO, keep m equal to 1, p equal to 1, that is input variables m equal to 1, output variable p is equal to 1. We'll get a constant at the matrix. So next topic is state space representation by physical variables. So how do you represent this physical variable in terms of state variables? So what do you know the state of this particular circuit? It purely dependent on the inductor and capacitor of the circuit. Since they are frequency dependent elements. So how do you represent state of this particular circuit diagram? So the information at any time t can be obtained if the initial voltage across the capacitor and the initial current through the inductor are known, in addition to the values of the input obtained for t greater than 0. So to represent this, we should write the Kirchhoff's voltage law equations and write in the form of state model. So what is state model? Which is x dot of t, very important equations, and b into u of t, and the output equation y of t is equal to c into x of t plus d into u of t, right? So here the output would be ec of t. This is your output y of t. It was represented as y of t. And what is the input? Input is e of t. Right? So what are the variables here? Here you have some RLC elements. Right. First, let us write the KVL equation for the circuit, RLC series circuit. So what is the KVL equation? Here I write apply KVL to the circuit, it would be R into I of t is L into df dt plus, so what's the voltage across capacitor? It is denoted as EC of t, which can be equal to E of t, right? So if you look at our state model, your state variable. So now what are the state variables here? State variables are inductor and capacitor. Since your circuit state will purely dependent on the inductors and capacitor of the circuit, right? So let us rewrite this equation number 1 as di by dt is equal to minus R by L into I of t minus 1 by L into EC of t plus 1 by L into E of t, right? Yeah. So let it be equation number 2. Why I'm writing like this? Your state equation is x dot of t, that is first order differential equation. So it is first order differential equation. Let us write the next equation in the circuit. That is current through capacitor. What is the current through capacitor? I of t is equal to C into d EC of t by dt, right? So rewrite this equation, it will be d EC of t by dt is equal to 1 by C into A of t. This is the fourth equation. Okay. Now look at the equation number 2 and 4. Equation number 2 and 4. Can we put these two equations in a matrix form? Yes, we can put it in matrix form, like di of t by dt and dEc of t by dt. So let it be is equal to, can we write minus R by L minus 1 by L 1 by C. I think I can put 0 here into I of t and EC of t plus 1 by L into 0 E of t, right? So what is this? Let us write the first equation. X dot of t is equal to A into X of t plus B into U of t. We call this. Now compare this equation with your matrix. What is X dot of t? This is di of t by dt by dt and d ec of t by dt, and this is your A matrix. And what are the state variables? As I mentioned, the state variables are the current through inductor and voltage across capacitance. It will give you the state at any point of time, right? Yeah, and it is purely dependent on the voltage across the capacitor and current through the inductor. So that's why these two are the state variables. What are the state variables? This one and current through inductor and voltage across capacitor. And this is matrix A, and this is x of t, and this is your x dot of t plus, and this is your b, and this is u of t. So what is u of t? Your input. Input is your u of t. So this is how you can represent your circuit elements by this state equation. Okay. So let us write the, so how do you obtain the state model? We should have both x dot of t is equal to a into x of t plus b into u of t, and y of t is equal to c into x of t plus d into u of t. So I need state variables equation and output equation. Now what is the output equation in this circuit? What's the output equation? So the output is equal to output equation y of t is equal to voltage across the capacitor. Right. Now how do I represent this equation? Like your y of t is equal to c into x of t plus d into u of t. Right. Now what is x of t? We know what is x of t. X of t is nothing but your current through inductor and voltage across capacitor. So this is your x of t, and it should be multiplied with C matrix. Can we write like this? This could be your y of t or output C of t, right? So what is this? Sorry, I wrote it in the wrong way. We will reverse it. 0 and 1. Now what is y of t? You multiply with 0 and I of t, it will be 0 and 1 EC of t, which is equal to your EC of t, right? Now you compare this equation with your state model equation. Your C matrix is this is your C matrix, and this is your x of t, and plus you don't have anything, so that's why D matrix is 0 and input is 0. So this is your output equation, and this can be represented like that. Okay. So this is how you can represent the variables, state variables, by physical variables. Okay. So only thing is you write the equations in the circuit diagram by applying KVL and KCL and put it in the state model equations. That's it. So first thing is, first identify state variables. That is current through inductor and voltage across capacitor. Voltage across capacitor. Yeah, XV panel. So once you identify current through inductor and voltage across capacitor, you will get the state variables. Then identify the next step, identify input and output, right? And third step, put in the state model equations. That's it. So that's enough. No need to find out the solution like finding current and voltage across the capacitors and inductors. No need to find the solution of the circuit. You just represent your variables in terms of state model. That's it. So let us look at one more example to understand this state space representation by physical variables. Let us consider one more example. This time I can say I capacitor, one more inductor, one more capacitor, and one more resistor. Okay. So let us write the names here. R1, and this will be R2, C1, and this is C2, CGL, since we have only one. So let us represent the current since your input is. So this is your input, obviously. So let the current through this R1 is I1 and C1 is I2 and this is I3, let us say, and assume this is I4 and this would be I5. Okay. So this is your second example. So first thing is identify the inductors and capacitors in this circuit diagram. So we have two capacitors and one inductor. Obviously, we have three state variables. So what are those three state variables? Let us write this voltage also. Let it be V1 here and this would be V2. So that you can easily find the state variables. Now what is the state variables? Voltage across capacitor and current through inductor. So what are the voltage across capacitors? Well, it is dV1 by dt, comma, dV2 by dt, and dI3 by dt, right? So now these are the state variables. So we should represent these variables, state variables, using state model equation. So what are the state model equations? X dot of t is equal to A into x of t plus b into u of t. And then y of t is equal to c into x of t plus d into u of t. Right? Now how do I write the equations? But, first of all, write the input. What is the input? input is AFT. So what is the output? So output generally, if you don't have any output given in the circuit, let us take the last element voltage and current. That is, what is the current through what to? It will be I5. And what's the voltage across resistor? It will be V2, right? If it is given output, you should take that value as in output. And then, so let us write the KCL at this point, right? So it's apply KCL at the node here, at node 1. So let us say node 1 is this, and this is node 2. So it's the KCL, apply KCL, that is I is equal to I1 plus I2 plus I3. So first equation. Now what is I? Can write it as, what is I1? I1 is nothing but current through resistor. Can we write like this, V1 by R1 plus, so I2 could be C into or C1 into dV1 by dt plus, I'm keeping I3 as it is. Look at this equation. I need dV1 by dt, I got it. And it is in terms of x of t, that is state variable. What is the state variable here? One is I3, V1 and V2. So I got V1 and V2, I3, and also I got the differentiation of the V1. So I can rewrite this equation as dV1 by dt is equal to minus V1 by R1 C1 minus I3 by C1 plus I by C1. So let us put this as equation number 1. Okay. So I got, I think, one state variable, different first order differentiation of the state variable dV1 in terms of state variables and input, right? These are all state variables and input. Similarly, write the second equation, apply KCL at node 2. So here, apply KCL at node 1 here. Now apply KCL at node 2. So what is the KCL here? Your I3 is equal to I4 plus I5, right? Look at this. I3 is equal to I4 plus I5. Now what is I4? I3 is equal to, so I4 is C2 into dV2 by dt plus, what is I5? V2 by, so I can put capital V2 by R2. Okay. I think I got dV2 by dt. Again rewriting this equation, I got dv2 by dt is equal to minus v2 by part2 c2 plus a3 by c2. This is equation number 2. I think I got two equations. The one more equation left is di3 by dt is to obtain the supply KVL around this loop. Apply KVL for this loop. So here so it would be voltage across inductor, or I can say, let us look at this. To take this loop, and this is drop voltage, again this is drop voltage, and this could be the rise voltage since your current is going opposite to your loop. So voltage across capacitor V1 is equal to sum of the voltages across inductor and C2. So it would be V1 is equal to L into di3 by dt plus V2. Again, rewriting this equation, you will get di3 by dt is equal to minus V2 by L plus V1 by L. This is your equation number 3. See, I got all the state variables, first order equations, first order differential equation. Now put them into matrix form. So put 1, 2, and 3 in matrix form. What are those? I can write it as dv1 by dt, dv2 by dt, di3 by dt. Which is equal to so here we get minus 1 by R1 C1 0 0 1 by L 0. Now what are the state variables? V1, V2 and I3. You should have this order. This must be fixed. Plus the input is 1 by C1, the other terms are 0, which is I. Yeah. Right? I hope you understood. This is x dot of t is equal to this is A matrix into x of t plus B matrix into U of t input matrix. Similarly, for output variables, now what are the output variables mentioned here? Output variables are I5 and V2, right? So I can also write them as I5, V2 is equal to, can write like this, right? 0 V1 V2 and I3. So that is the matrix is 0 here also. We don't have any input multiplied by some D matrix. So it would be y of t is equal to c into x of t plus d into u of t. So in this case, I don't have this term. So that's why this term is 0. And you have C matrix and this is your x of t, right? So this is how. So you can represent your output variables using state space equations or state model. Okay. So I multiply with this, I will get I5 by R2 is nothing but your V2 here. So other terms you will check, you will get the output equation, right? So this is how you can represent by physical variables. Now let us look at the state space representation by phase variables. Next part. State space representation by phase variables. Okay. So physical variables, it's very easy. So once you have inductors and capacitor, you can easily find out the physical variables. You can easily represent by applying KVL and KCL and put them in matrix form. What about phase variables? So they are defined as those particular state variables which are obtained from one of the system variables and its derivatives. So let us write the definition of the phase variables, then we will find the phase variables for representing the state space equations. Right. So let us define the phase variables are defined. They are defined as those particular state variables which are obtained from one of the system variables. And its derivative. Why I'm writing, we use this definition to obtain phase variables. So what are the key points here? So they are defined as the particular state variables. They are also state variables, but they are very particular state variables which are obtained from, again, one of the system variables and its derivatives. Right? So normally what are the system variables? So the system variables are input variables or output variables. So here we'll take output as the system variable. So consider output as a system variable and we'll take the derivative of the outputs. So that's how we represent phase variables in terms of output variables and its derivatives, right? So the second point in this phase variables, normally the system variable used is the system output, and the remaining variables are derivative of the output. Now, what are the key points here? Now the system variable used here is your output, and the remaining variables we use the derivative of the output, right? So generally phase variables are not physical variables of the system and therefore are not available for measurement and control purpose. So then we assumed some system variable and we'll take some derivative of the output variable. So they are not available for measurement, but phase variables establish the link between the design approach and time domain design approach, that is transfer function design approach and time domain design approach. Right. So the general form of nth order linear continuous time system is, we have some equation. So how do you represent this general form of the nth order linear continuous time? So I'll rewrite here. We have already this general format. So what is that? The general form of the linear time invariant system is, oh, I use red color for this. Y to the power of n plus, you must all remember this equation, a1 into y to the power of n minus 1 plus a2 into y to the power of n minus 2 plus a n minus 1 into y to the power of 1 here plus a n into y to the power of 0. Which is equal to b naught into u to the power of n plus b1 into u to the power of n minus 1 plus b2 into u to the power of n minus 2 plus b n minus 1 into u to the power of 1 plus bn into u. Now what are these a1, a2, a3 and b1, b2, b3? They are constant. What is n? So n is nothing but your nth order differentiation. So let us represent this as what is y to the power of n. I'll write it here. A's and b's are constants, and y to the power of n is what is the meaning? This is the nth derivative with respect to time. This is the nth order differentiation. So for linear time invariant system, the change does not depend on the initial value. So we can find the transfer function as right here. The transfer function. So what is the transfer function? Output by input Laplace transformations is equal to what is that? B naught into s to the power of n. So if you take the convert into Laplace transformation, you will get s to the power of n plus e1 into s to the power of n minus 1 plus b2 gets to the power of n minus 2, right? Plus and so on, plus b into n minus 1 plus by here s to the power of n plus a1 Now, what are these terms? Sorry, forgot. Yes, here. What are these terms? The transfer function, just apply Laplace transformation both sides for this general equation, general linear time invariant continuous equation. You get these S terms. Now, what are the numerator values? These are all input functions with some derivatives, right? So let us consider the state space representation of nth order system in which the force function does not involve its derivative terms. So what's the first condition? So we have two types in this phase variables, uh, which involve the forcing function and does not have forcing function. The first one is first representation. This is about introduction part. Let us look at the state space representation of nth order system in which the forcing function does not involve its derivative terms. Just a minute. So let us find out the nth order system in which the forcing function does not involve its derivative terms. Now, what are the derivative terms in the transfer function, in this transfer function? So these are all derivative functions, right? Which has s terms. Okay. So we should not have all these derivatives. So since it's a forcing function, right? Your u of s is your forcing function input. So I can rewrite this equation as, therefore, the t of s would be, I have only one term, that is b to the power of n. Sorry. Oh, sorry. Skipping this. T of s is equal to bn by the denominator is s to the power of n plus a1 into s to the power of n minus 1 plus a2 into s to the power of n minus 2 plus and so on. So a n minus 1 into s plus an. Okay. So if you rewrite this equation again in time domain, it would be something like this. Rewriting in time domain. It would be y to the power of n here plus a1 into y to the power of n minus 1 plus a2 into y to the power of n minus 2 here plus 3 dots a to the power of n minus 1 into y to the power of 1 here plus which is equal to bn, right? So rewriting this equation is in time domain. Now, this is nth order differential equation. So we need n state variables to represent this system, right? So I can write it here. Since This is nth order differential equation. We need n state variables. So now what are the state variables? We represent generally the state variables, that is x1, x2, x3 and so on, xn. So we need these n state variables. Now look at the phase variable definition. So what is that phase variable definition? They are defined as those particular state variables which are obtained from one of the system variables and its derivative. Now, what is the system variable used in the system? It is output. And the remaining variables are derivatives of the output. So, first we should assume the first variable as the output variable. So, let the first variable, state variable x1 is equal to y, right? And the next state variable x2 should be the derivative of the output. So I can say this is y dot, right? And the third variable x3 would be y double dot, right? And I'm putting three dots here, x to the power of n minus 1. So what is the value here? It is to the power of n minus 2, right? It is n minus 1 here, n minus 2. So what is xn? Last variable, it should be y to the power of n minus 1, right? So this is about the state variables. Now what is this x1 dot? But what we need x1 dot, x2 dot, xt dot to represent the state model. So here I'll write what is x dot 1 is equal to. Take the differentiation of this. So it should be y dot. Now what is y dot? Y dot is x2. So what is this? x2, right? Similarly, what is x2 dot? Should be x y double dot, which is x3, right? So what is x3 dot? Y triple dot. So what is y triple dot? It is x4. Similarly, what is x n minus 1 should be xn. To understand this, I took some derivative from left side and I again wrote in state variables. Okay. Now what about the last value, that is x dot n. See, I stopped at this point, x dot n minus 1. What is x dot n? So this must be y to the power of n, right? Now what is y to the power of n? Which is nothing but bu minus a1 into y to the power of n minus 1 minus A2 into y to the power n minus 2 minus A3 into y to the power n minus 3 and 3 dots here, A to the power of n minus 1 into 1 minus an only, right? So now how do you get this equation? Look at the equation number 1. Now what is this equation? Oh, sorry, here I forgot this u here, right? Bn into u, right? So y to the power of n is equal to, these are all negative terms, and this would be the positive term, right? I wrote the same here, which is the last term, b into u minus a n minus 1 minus n, right? Look at this. This is the only key point in this phase variables, this equation. Writing the last equation. Yeah. Okay. So once you get the first order differentiation of the state variables, you can easily put them in matrix form, right? State model form. So we'll see this in the next class by taking an example. Okay. So if you have any questions, you can ask till this point. So let us put this in matrix form in the next class.